So we have this thing called the derivative, which is the instantaneous rate of change. And it's very important for us to be able to calculate it. In the last section, we developed some rules to help us start calculating derivatives easily without having to go through the entire limit definition every time we want to do a problem. Yes, we prove the rules and we use the definition of the derivative as a limit, the definition that makes it the instantaneous rate of change. We do that once in the proof, but then we just remember the simple rule. The rules that we have so far, there are basically only three of them. We have that the derivative of a constant is 0. We have linearity, which tells us that if you have a constant times a function plus a constant times another function, and you take the derivative, then you can split up the sum and pull out the constants. And for that matter, because b could be a negative constant, you could split up differences too. So this is linearity, that this splits up as a times f prime plus b times g prime. So it just means you reduce this complicated, the derivative of this more complicated looking thing, to having to know the derivatives of each of these more simple pieces. And then we had the power rule for integer powers, or positive integer powers. The power rule for natural numbers, so positive integers. And actually we said you could interpret it as holding even when the exponent is 0, with, if you're just careful, if you just agree to mean the right thing when x is 0. The power rule says the derivative of x raised to the nth power is n x to the n minus 1. And here I mean for I'll say an integer greater than or equal to 0. But yeah, when n is 1, and you have x to the 0 over here, you need to interpret x to the 0 as meaning 1, even if x is 0. And when n is 0, you'd get 0 times x to the minus 1. You need to interpret that as being 0, whether x is 0 or not. Because what we mean when n is 0 is just that this is 1 and the derivative of 1 is 0 because it's a constant. And we're just trying to incorporate this here. Or really it's this combined with this. You can pull out the c and then just be left with the derivative of 1, and that's handled by this. All right, these are the rules we have so far, and they enable us to differentiate any polynomial. So that's nice with ease. Now we can differentiate polynomials almost as fast as we can write, or as fast as we can write. The derivative of a polynomial, you pull out the constants and you just treat each summand separately. So the derivative of x to the 5th by the power rule, the 5 comes down, you subtract 1 from the exponent, plus a 7 times, you bring down the exponent, you subtract 1 from the exponent, plus the square root of pi is just a constant. The 2, you bring down the 2, you get 2 times the square root of pi times x to the 1, but that's just x, and then the derivative of a constant, 0. So you get this for the derivative. Yes, you can neaten it up. It's 15x to the 4th plus 21x squared plus 2 times the square root of pi x. But this is the answer. You don't use the limit again. We used it in the proof, and that's what makes this the instantaneous rate of change, that it's a limit of average rates of change. But now we can calculate it very quickly without ever mentioning the limit. Well, I mentioned it, but you don't need to do the calculation. But there's still some very simple derivatives, a number of very simple derivatives that we don't know how to calculate. For instance, could we calculate the derivative of a product in some easy way? Like, for instance, without multiplying the two terms together, can we somehow, by knowing the derivative of, can we differentiate this product? We know the derivative of this. We know the derivative of this. They're polynomials. we can differentiate them both easily. Yes, we could multiply this out and differentiate, but can we differentiate this without multiplying it out, because somehow using that we know the derivative of this and the derivative of this? You might suspect, the linearity was so simple. The derivative of a sum, you just split it up and it's the sum of the derivatives. You might think, the derivative of a product. You just differentiate each one and you multiply those together. It turns out it's not that simple. You might think, well, why don't you define it to be that simple? Because it's defined by the limit. The limit definition of derivative, the thing that makes the derivative the instantaneous rate of change. And we don't just get to make up the rules, we have to figure out what they are based on the definition, and we have to prove something. So it's not as simple as you take the derivative of this and multiply it times the derivative of this, but it's not too bad. Then there are derivatives of quotients. So suppose you had x squared minus 1 divided by x squared plus 1. We don't know how to differentiate this yet easily. You know the derivative of the numerator, you know the derivative of the denominator. Does that in some way tell you what the derivative of the quotient is? It does, but again, it's not obvious. And the answer is not, you differentiate the numerator and divide by the derivative of the denominator. It's not that simple. It's significantly more complicated. What about the power rule? We don't know the derivative of x raised to negative powers right now, negative integer powers. Why not? Because we only proved the power rule in the positive integer case, and then we said, and when n is 0, if you interpret it correctly. But we don't know how to differentiate this. This is the same as the derivative of 1 over x to the 5th, and so if we knew how to differentiate a quotient, we would be able to differentiate this because we differentiate as the quotient of something we know, and again, by something we know. So this is what we're after today, the product rules and the quotient rules. How do you differentiate a product if you know the derivative of each factor? How do you differentiate a quotient if you know the derivative of the numerator and the derivative of the denominator? So the product and quotient rules tell you these things. So let me state them. I'll prove the product rule for you just so you can see that we don't make these things up, and because it's relatively easy. There'll be plenty of things throughout the book that we don't prove or even give you a hint of a proof of because they're really complicated and technical, but the product rule is not bad. Neither is the quotient rule for that matter. So theorem. Suppose f and g are both differentiable at x, so their derivatives exist. Suppose f and g are differentiable at x. Then we have the product rule. And it says that, so this is the product rule, then f times g is differentiable at x. I'll abbreviate, is differentiable at x. And the formula for the derivative, so what's the derivative of this? You can memorize this with the f's and g's in it. I suggest that you not. I will say the first thing and the second thing. You could say the first factor and second factor, but thing has one syllable and it's just shorter and it's easier to remember. So it's the first thing times the derivative of the second plus the second thing times the derivative of the first. The problem with memorizing this formula with the letters in it is that if you have different letters, it might be hard for you to change. I suggest saying first thing and second thing, or first factor and second factor in your head or out loud or whatever it takes. And then there's the quotient rule. Which says, it says something about f divided by g. We certainly need g of x to not be 0 so that f over g is defined at x. So if g of x is unequal to 0, then f divided by g is differentiable at x. And its derivative, this looks significantly worse. It's not that bad. Also, the words numerator and denominator are far too long to say. And again, though, you don't want to memorize it with f's and g's in it because you might have other functions. So I suggest the following: the bottom times the derivative of the top minus the top times the derivative of the bottom, all divided by the bottom squared. These are the product rules and the quotient rules. We're going to do a bunch of examples with them. But I first would like to, actually maybe I'll give you, I was going to say I'll prove the product rule first. Let me go ahead and give you the power rule for integer powers, and then I'll come back and prove the product rule for you, and then leave the quotient rule as an exercise or something for you to read in the textbook. So, we immediately conclude from the quotient rule and the power rule for natural powers, the power rule for integer powers. So, including negative integers for integers n. It says exactly the same thing. It's just that now n gets to be a negative number. It says you bring the exponent down as multiplication and you subtract 1 from the exponent. So, for example, the derivative of x to the minus 5 would be minus 5 times x to the, you subtract 1 from the exponent, x to the minus 6. Why is this true? It's easy to get from the quotient rule. So all we need to do is show that this is true for negative exponents, because we already know it's true for non-negative exponents. So let's look at the derivative of x to the minus m, where m is positive. We'll just go ahead and say positive. So it's a positive integer, so it's a natural number. So that negative m really is negative. How do we find the derivative of this? We write this as 1 over x to the m. Then we calculate its derivative from the quotient rule, which says this is the bottom times the derivative of the top minus the top times the derivative of the bottom, all divided by the bottom squared. But this is the derivative of a constant. That's 0. 0 times x to the m, 0. Minus 1 times this, m is a positive integer. So we know how to differentiate this by the power rule for natural numbers. This is m x to the m minus 1. And then you divide by, well, this is, you raise an exponent to an exponent, the exponents multiply. This is x to the 2m. So you get a minus m. And then when you have a base raised to a power divided by the same base raised to a power, the exponents subtract. So you get x to the m minus 1 minus 2m. But this is minus m x to the minus m minus 1. But that's what we were trying to show. That's the power rule. It means that what's the derivative of x to the minus m? The minus m comes down, and you multiply by it, and you end up with an exponent that's 1 less than what you started with. You start with minus m, now you have minus m minus 1. So now we have the product rule, the quotient rule, and the power rule for integer powers. All right. Let me give you the proof of the product rule, just so you can see that we don't make these things up. You must use the definition of the derivative, the definition that makes the derivative the instantaneous rate of change. and see why it comes out to be this way. It's kind of cool. Cool in that math dork sense of the word cool. So why does the product rule work out that way? Well, we want to calculate this derivative. That's the limit as h approaches 0 of, you replace the x's by x plus h. You subtract what you had at x. And you divide by h. And then we use mathematician's stupid trick number 1. Mathematician's stupid trick number 1, add 0 in a clever way. Mathematician's stupid trick number 2 is multiply by 1 in a clever way. But number 1 is add 0 in a clever way. What is the clever way to add 0 here? The clever way is to subtract f of x plus h times g of x, and then add it right back again. And run out of space. All right, let's try that. Let me write this farther over. So you get f of x plus h. I have to write smaller. G of x plus h. And then I'm going to subtract f of x plus h times g of x, but then I'm going to add that right back. And then I still have to subtract the f of x times g of x. Why on earth would you do this? So what have I done? Why does this equal this? Because this part's the same, this part's the same, and all I did here in the middle was add 0, this part. I subtracted f of x plus h times g of x, and then I added f of x plus h times g of x. I added 0. So clearly I didn't change anything. How could this possibly be useful? It tells us how to split up this limit in a nice way, because we can split up this part and this part. So we've got this fraction. It's got a sum in the numerator. We can split up the fraction and write, this is the limit as h approaches 0 of, you get the f of x plus h times g of x plus h minus f of x plus h times g of x, that part divided by h. And then there's plus this part divided by h. So plus f of x plus h times g of x minus f of x times g of x, all divided by h. How does this help? This may look much worse to you. Actually, it shouldn't, because there's an f of x plus h term here and here that we can factor out, and a g of x term here and here that we can factor out. And what you're left with, after you factor those things out, are two things that look very much like the limits that occur in a derivative, which of course is where the product rule comes from. So what do you get? You get the limit as h approaches 0. I'm going to split up this sum as the sum of two limits. And it's a limit of a sum. That's the sum of the limits, provided each of the individual limits exist after we split it up. But we'll verify at the end that the limits exist, so this will be right. So you take this part, and I'm going to factor the x plus h out. And so I get the limit as h approaches 0, f of x plus h times, what we still have is g of x plus h minus g of x over h. And then you also get, that's added to the limit as h approaches 0 of, and in this part, you factor the g of x out. So you get g of x times f of x plus h minus f of x over h. And now we're essentially done. As h approaches 0, as h approaches 0, this is g prime of x. This limit as h approaches 0 of this part is g prime of x. As h approaches 0, this approaches f of x because f has to be continuous at x because it's differentiable there. That's a technical point, but an important technical point. Because f is differentiable at x, f is continuous at x, which means that as h approaches 0, f of x plus h approaches f of x. And so this part becomes f of x. The limit as h approaches 0 of this part is g prime of x, plus this part is a constant as far as h is concerned. It doesn't change as h changes. This is g of x, and then times the limit as h approaches 0 of this part, that's f prime of x, the derivative of f with respect to x. And that's the product rule. The derivative of the product. It's the first thing times the derivative of the second, plus the second thing times the derivative of the first. All right, enough theory, enough rules. Let's do some examples. So, an example of using the product rule. We don't have that many functions yet. We haven't talked about sine and cosine, logarithms, and raising fixed bases to powers. So, but we can do products of polynomials. In fact, if I want to match the examples that are in the book, let's look at this example. Let's calculate, so suppose x is 5t squared plus t minus 2 times t squared minus 7t plus 3. To put this in physical terms, x might be the position of an object in meters. And t is the time in seconds. And the question is, can you calculate the velocity without the velocity of the object without multiplying these two things together? Yes, we can multiply them together, get a polynomial, and differentiate using the product rule, using the power rule and linearity. But can we do it without it? Yes. The velocity, v, the velocity. Velocity is the instantaneous rate of change of position with respect to time. It's dx dt. So it's the derivative of this product. To calculate the derivative of this product, you use the product rule. It is the first thing times the derivative of the second. So the first thing times the derivative of the second. I'll just write the derivative of the second thing, but I won't calculate it yet. First thing times the derivative of the second, plus the second thing, the t squared minus 7t plus 3 times the derivative of the first thing. Then what do you have left to do? You have to calculate these two derivatives, right? This part, we don't have to differentiate this, but this, we have to calculate the derivative of the stuff in the parentheses. This part stays the way it is, but we have to calculate the derivative of this thing in parentheses. So it boils down to we have to know the derivatives of the two factors. That's not a surprise. So what do you get? Well, we know the power rule, we know linearity. It's easy for us to differentiate now. We get 5t squared plus t minus 2 times 2, t to the 1. Okay, that's a 1, not a prime. It's important to make your primes slant so that they don't look like 1s. Minus the derivative of 7t, but that's just 7 times the derivative of t, which is 1, plus the derivative of 3, which is 0. So we just get this. And then you add to that plus t squared minus 7t plus 3 times the derivative of 5t squared plus t minus 2. That is 5 times 2t to the 1 plus 1, and then plus the derivative of negative 2, but that's 0. So this is what you get. You know, don't leave the, oh, this is meters per second, of course. The units on the derivative, you should never forget this. The units on your derivative are always the units of that variable divided by the units of that variable, so meters per second. This is in meters per second. You don't need to write the raised to the 1 power. That's just the same as t. 5 times 2, 10. I'd leave the answer like this. I mean, you could multiply it out, but if you're going to multiply this out, you might as well multiply it out the thing you started with and differentiate it that way. So I just leave it like this. Okay, there's one example of using the product rule. What about using the quotient rule? So suppose you've got v, the velocity. So suppose in another problem, you've got the velocity of an object. And just to change our units, we'll use feet per second for the velocity. And it's given by t squared minus 1 over t squared plus 1, where t is in seconds. So t is in t equals the time in seconds. We can ask, what's the acceleration of the object at time 2 seconds? Well, acceleration. Acceleration is the instantaneous rate of change of the velocity. But we've got the velocity, so the acceleration at any time is the derivative of the velocity with respect to time. That is t squared minus 1 over t squared plus 1 prime. And now you use the quotient rule. You get, this is the bottom, the t squared plus 1, times the derivative of the top. The derivative of the top, you get, by the power rule, you get 2t to the 1. You bring the exponent down as multiplication. You subtract 1 from the exponent. You get 2t to the 1. That's just 2t. Minus the derivative of 1, but that's 0. So you just get this. That's the bottom times the derivative of the top. Then there's minus the top times the derivative of the bottom. What's the derivative of the bottom? You get a 2t again, and then the derivative of plus 1, but that's 0. So you just get a times a 2t all over the bottom squared, which is t squared plus 1 quantity squared. Just leave it that way. You don't want to expand this. You could expand it as t to the 4th plus 2t squared plus 1, but it looks better like this. So, you could, this is the answer. There are no derivatives left. But we might want to simplify it a little bit. In general, the instructions simplify as difficult to make precise. What looks more simple to one person doesn't always look more simple to another. But let's neaten this up a little bit. You multiply this out, you get a 2t cubed plus 2t. And then you get minus, and then you get another 2t cubed. And then there's a minus minus, that's a plus, so plus 2t. the 2t cubes cancel, and you're left with 4t over t squared plus 1 squared. Units, feet per second per second. That's the acceleration at any time t. The problem asks for what's the acceleration at time 2 seconds. So we want a at time 2, or dv dt, when t equals 2. That just means you plug t equals 2 into this, so you get 8 over, you get 2 squared, 4 plus 1, 5, 5 squared, 25, 8 25ths feet per second per second. All right, so that's an example of using the quotient rule. What's an example of using the power rule for negative exponents? Well, any problem with a negative exponent, but let me mention a particularly important physics law, kind of like we've talked about Newton's second law of motion before, and I will come back to that in a few minutes. But there's another law due to Newton, the law of universal, or there are probably a bunch of them, the law of universal gravitation. And what this says is the force, the gravitational force exerted by one mass on another. So we've got, this is one mass, and use a capital M because you're thinking of it as kind of the big mass, like a planet or something. It doesn't have to be, it's just the mass of one of the things you're talking about. And then you've got another mass, so another object that has some mass. You know, usually something smaller than a planet, but they could both be planets or stars or something. It's the force that gravity exerts, the force of gravity between the two masses, is some universal constant, the universal gravitational constant, divided by r squared. So let me write what everything is. Where? So F is the gravitational force. I'll pick some units. I'll use newtons in newtons. I've already said that the m's are the masses, but now if I want my units to be consistent, these will be both in kilograms. R, this capital R, is the distance between the two masses, and because the masses aren't just points, you want to say between the two centers of mass of the masses. So R, capital R, is the distance between the centers of, between the centers of mass of, centers of mass of m distance between, let's try this, m and little m, and G is this universal gravitational constant and I do not have this memorized. It's approximately 6.674283 times 10 to the minus 11th meters cubed over kilograms second squared. All right. Okay, I'm not going to use what G is. I'm just going to keep calling it G because it's easier than writing that all the time. But what's a standard question here? Oh, let me change. I've written capital R in the text if I don't want this to be confusing. In the text, they've written a little r. I would hope that wouldn't confuse you even if I left it, but let me change it. So what's a typical question? What is the rate of change? Of the gravitational force between two objects, so fix capital M and M. What is the rate of change of the gravitational force with respect to the distance between the objects? So between their centers of mass. So what are we being asked for? We're being asked for what's df dr, the derivative of f with respect to r, the instantaneous rate of change of f with respect to r. Well, it's easy for us now. There's essentially nothing, we have very little work to do. Here's f as a function of r. We could use the quotient rule. It is a quotient, but the numerator is a constant. And since the numerator is a constant, and the denominator is just a power of r, the easier thing to do, instead of using the quotient rule, which isn't hard, but it's still, rewrite this before you ever start as GMM times r to the minus 2. Those are the same, algebraically, but now to differentiate, it's completely trivial. df dr, it's, well, the derivative of all of this, g, m, and m, all constants. So the derivative of this constant times that, you pull out the constant, so you just get the g, m, m. And then you have to multiply times the derivative of r to the minus 2. But we know how to differentiate that with respect to r. We just use the power rule. The exponent comes down as multiplication. You subtract 1 from the exponent, you get minus 3. We could write this a little more neatly, write it as a fraction, since we start with f that way, but what we get is minus 2 GMM, minus 2 GMM over r cubed. The units would be newtons per meter, or whatever, and if you were using different units, it would be your force units divided by your distance units. So the rate of change is, well, we could say inversely proportional to the cube of the distance between the objects. All right. Okay, while we're doing physical laws, why don't we switch fields and go to chemistry and look at the ideal gas law. So we have the ideal gas law. So it's frequently good to assume that a gas that you're working with is an ideal gas, which is a technical assumption on some properties of the gas. I'm not going to go into what it is. But many gases behave approximately like ideal gases. And so if you have an ideal gas in a container, and the container might have a variable volume, so it might be like a balloon or a piston in a car, something whose volume might be able to change. Maybe it's in a container with a fixed volume, but maybe it's not. Then there's a relationship between the pressure that the gas exerts on the walls of the container, the volume of the gas, and the temperature of the gas. I'm going to write it like this. This is the pressure exerted by the gas on the container. And again, I need to pick some units. I'll pick newtons per square meter. This would be the volume of the gas, so the volume of the container. We assume that the gas expands to fill the container. The volume of the container, this will be in cubic meters. This is the temperature, and it needs to be on an absolute temperature scale. So this is in kelvins. Which is abbreviated with just a K. I'll try to, it is not this K. That's a little k. I'm trying to make this a capital K. Try not to get those confused. These used to be called degrees Kelvin, but there was a convention, I don't know, 30 years ago, that we would stop saying degrees Kelvin and just say kelvins. And K is a proportionality constant that depends, well, on the fact that we have an ideal gas and on the amount of gas that we have, the number of molecules of gas that we have. But for a fixed problem where you have a fixed amount of gas, K is a constant. So K is a constant. Which is measured in, well, the units it needs to be measured in to make this all correct. So if we've got newtons per square meter times cubic meters equals K times something that's measured in kelvins. That's a little k. There's a capital K. Then the units on K, these would need to be Newton meters, so newtons times meters divided by kelvins. All right. So that's the ideal gas law. Who cares? Well, a lot of people care. But what happens in a real problem, in a real physical situation, is, especially if the volume of the container is allowed to change, that all three of those quantities, the pressure, the volume, and the temperature, might be changing with time. So maybe the gas is heating up and the volume's increasing and the pressure is increasing or decreasing. P, V, and T, capital T, are allowed to change with time. And so let me give you a typical problem where I pick some numbers and I want to agree with what's written in the book. So suppose at some time, T naught, I should make a comment. I just read this as T naught, and you may hear a lot of people say that. I am not saying not. I'm not saying N-O-T. I'm saying naught, N-A-U-G-H-T. It's what the British say for zero. So this is T naught, not T naught. All right. Suppose at time T equals T naught. P, the pressure, we know the pressure, and it's 100,000 newtons per square meter. And we know the volume of the container, and so the volume of the gas, that the volume is 0.02 cubic meters. And we know how fast the pressure is changing. We know that at time T naught, the rate of change of the pressure with T in seconds, well, so it'll be clear, is minus 100 newtons per square meter per second. What does this minus mean? It means the pressure is dropping at a rate of 100 newtons per square meter per second. Right? The dP/dt, the rate of change of P with respect to time, it's also the same as the rate of increase. That minus sign means it's decreasing or dropping. So the pressure is dropping at a rate of 100 newtons per square meter per second. And the rate of change of the volume with respect to time is 0.005 cubic meters per second. Suppose we know all that, and we know how much gas we have, and so I'll just assume, we're also going to assume that we know K, because we know how many molecules of the gas we have. We're going to assume that K is 8 Newton meters per Kelvin. All right, what's the question? The question is, okay, at that time T naught, how fast is the temperature changing? And is the temperature increasing or decreasing at time T naught? Now, you're not told any of these functions as a function of time. You don't know the volume as a function of time. You don't know the pressure as a function of time. You don't know the temperature as a function of time. All you know is this data, that at time T naught, you know the pressure, you know the volume, you know at that time, not at all times, you know how the pressure is changing at that time, you know how the volume is changing, and of course you know this constant K. The question is, can you say how the temperature is changing? It sounds like, so my question is, what is dT dt, the rate of change of the temperature of the gas at time T naught? Can we do this? We don't have a formula in terms of T for the temperature as a function of time. How on earth could we possibly calculate this derivative? And the answer is the product rule. We don't have to explicitly know what capital T is as a function of little t to use the product rule. What we know is that capital T is related to P and V by this at all times. And so, yes, they're all functions of time. And it means that the temperature, if we divide by K, is 1 over K times P times V. So yes, this is some function of time. This is a function of time. And if we knew those explicitly, we'd know capital T is a function of time. Can we answer the question anyway without knowing what any of those are explicitly as functions of time? The answer is yes. You just use the product rule. dT dt is, all right, this is a constant times that. So you just get a constant times the derivative with respect to t of this product. Okay, we don't know what these are as functions of times, but it doesn't matter. We know they're functions of time. We know they're differentiable at time t naught because we're given their derivatives at time t naught. So that means that this product is differentiable at time t naught and its derivative at that time. So needs to satisfy, it is the first thing times the derivative of the second. The first thing times the derivative of the second, plus the second thing times the derivative of the first. Right? So at time t naught, what do we get? You just evaluate everything at time t naught. And since you were told P at time t naught, dV dt at time t naught, V at time t naught, and dP dt at time t naught, you can fill in everything. So K is 8. P, I've lost it. P is 100,000. I'm going to drop the units until the end. P is 100,000. dV dt, we were told, is 0.005. This is only at time t naught. Right? If we were asked for the rate of change of the temperature at any other time, we wouldn't have the data for that. Plus the volume at time t naught, 0.02 times dP dt at time t naught, which is minus 100. And the units on this, the units are just kelvins, those units divided by those units, kelvins per second. I'm not really interested in what this number comes out to be, but Suppose we could work it out a little bit. This is the answer. It would be nice to know whether it's positive or negative, so that we know whether the temperature is increasing or decreasing, but actually calculating the number isn't terribly interesting. This is 5/1000ths. So if I multiply it times 1,000, I get 5. So this is 500 when I multiply these together. This is 200ths times minus 100, so you get minus 2. So you get 1/8 of 498. So I'm happy to leave it like that. It's not like we couldn't do that division, but it's positive. So the temperature at time t0, the temperature is increasing, and it's increasing at that rate. Okay, let's do one last example of using the product rule. In a way, it's similar to our use in the ideal gas law, in that I'm going to apply it to a physics formula where we don't have an explicit formula for how anything's changing with time, and still the product rule tells us a lot. So I want to come back to something I've mentioned before. Newton's second law of motion. I remind you that it says that the sum of the forces acting on an object equals the rate of change of the momentum with respect to time. So, sum of the forces acting on an object equals the rate of change of the momentum of the object. With respect to time. In letters, well, using variable names, this sum of the forces is usually just called F. Momentum is the mass times the velocity. So m is the mass, v is the velocity. So in letters, as a formula, what this says is the sum of the forces equals the derivative with respect to time of the mass times the velocity. The standard case in which people apply Newton's second law of motion is to problems where the mass is constant. You're talking about a fixed mass. But there are important problems where the mass is not constant. For instance, and I've said it before, for instance, rockets. Rockets expel a large portion of their mass as they burn fuel. Hail dropping through the atmosphere, ice gets bigger around the hailstone. You say that ice accretes, and so the hail gets bigger. Snowballs rolling down a snowy hill, the mass of the snowball gets bigger. There are lots of problems where the mass changes, but the standard use, in the standard case, m is constant. So you have a constant mass. And then this becomes F equals the derivative with respect to time of m times v. But we know that the derivative of a constant times something, you just pull the constant out and take the derivative of the other thing. So you get the mass times the derivative of the velocity with respect to time. But this is the instantaneous rate of change of velocity with respect to time. That's the acceleration. And so you get the very famous, easy to remember, F equals ma. The sum of the forces equals the mass times the acceleration. But what happens when the mass is changing with time? This is important, and it's not so many people know this. This one, it's you have to use the product rule. If both of these things are changing with time, then this is the product of two functions of time, and you're taking the derivative. You have to use the product rule. It is the first thing times the derivative of the second, plus the second thing, the v, times the derivative of the first. And it's true that this part, the m dv dt, is still ma, but you get an extra piece. The sum of the forces would need to be bigger. You get an ma, but you get plus a v dm dt. Well, bigger assuming v is positive and dm dt is positive. Right? Here's the F equals ma part, but then there's plus v dm dt, which you can't ignore if dm dt is not 0. And when would dm dt not be 0? When the mass is changing with respect to time. So keep that in mind. These are cool uses of the product rule where you don't actually have explicit functions of time and still you get important results from the product rule. We'll use the product rule, the quotient rule, and the power rule for integer powers throughout the remainder of the book. Next time, we will do the chain rule. The chain rule tells you how to differentiate compositions of functions. And then we'll be through with our general rules, but we'll still need to deal with a bunch of very specific functions like sine and cosine and inverse trig functions and exponential functions. All right, but that's it for this section.